Welcome to Lecture 20, in which we will learn about the PAL. That's PAL, which stands for Programmable Array of Logic, as you can see here. The example that I'll be using here to explain this concept is from the Gavone book that I've mentioned previously. So here is an example of what the PAL looks like, and I should add in a little bit more information here. In the particular example that I want to look at, I'm going to put in some connections here, and once I put in these connections, you will see immediately the way in, or some of the ways in which this differs from a prom. Okay, so if we look at this closely, you notice that one of the differences between the PAL and a prom is the fact that in the prom, it is the connections down here in the OR array. We'll call this the OR array. It is the connections down here in the OR array that are programmable, and the connections up here in the AND array are permanent. That's in the prom. But here in this situation for the PAL, it is the connections down here in the OR array that are permanent. You can see we're using the solid circles to denote that these are permanent connections. And so it's up to you to decide how to program the PAL by making connections up here in the AND array. And another thing, if you're looking very closely, another thing you'll notice is that in the prom, remember that the number of AND gates was equal to 2 to the n, where n is the number of input lines. But here we have 4 input lines and only 8 AND gates. So this means that if we have a different input, let's say, suppose we had the variables w, x, y, and z, which were 4 independent variables, then we would not be able to have all of the possible minterms of those 4 variables with just 8 AND gates, because of course when you have 4 independent variables, there are 2 to the 4th or 16 possible minterms. So these are some of the differences between the PAL and the prom. And so in the example that we want to look at here, our goal is the following. We want to use the PAL that's pictured here to realize the following functions. We have F1, so this is, we might say this is our goal. We want F1 of XYZ to be equal to the sum of the minterms 1, 2, 4, 5, and 7. And we want F2 to be the sum of the minterms 0, 1, 3, 5, 7. And even though a function f3 is shown, nothing is specified at the following time. Now, if you look carefully at what we've stated here as the goal, you will see that there's a problem. And the problem is this. F1 is expressed here as the sum of 5 minterms. However, down here, we're summing up only 3 terms. Likewise, F2 is the sum of 5 min terms, but it as well is the sum of only 3 terms. So our problem is that it almost looks as though we can't achieve this, but of course we remember that earlier in the course we have been learning about minimization, and so the immediate idea that occurs to us is to see if we can write F1 and F2 more simply than they are written up here. In other words, can we write them as the sum of a smaller number of terms than 5? In fact, we would like to write F1 and F2 both as the sum of 3 terms. So let's see if this can be done, and let's start with F1. So F1 is a function of 3 variables. So we will draw a kernel map with 8 cells. And again, this will be F1, so I'll put F1 there. Actually, I think I'm maybe not leaving enough room here, so let's come down here. So F1 is a variable, a function of the variables x, y, and z. So we put x on the vertical axis and y and z on the horizontal axis, and number the kernel map in the usual way. And then we remind ourselves that F1 is the sum of the min terms 1, 2, 4, 5, and 7. So going through here, going through this kernel map in the usual way, this is cell 0, this would be cell 1, so we put a 1 in here, and then this would be cell 2, so we'll put a 1 in there. This would be cell 3, and it's not present in the function, so now we want 4, 5, and 7. Here is cell 4, so we'll put a 1 there. Here is cell 5, so we will put a 1 there. And cell 7 is right here, so we'll put a 1 there. And that's the kernel map for F1. And as long as we're at it, we can go ahead and draw the kernel map for F2 as well. Now for F2, we recall looking above that F2 is 0, 1, 3, 5, 7. So 0, 1, 3, 5, and 7 looks like that. And that completes the kernel maps for the functions F1 and F2. And now we try to use these kernel maps to see how we might be able to write these two functions as a sum of hopefully 3 terms. So let's see what happens. Okay, starting with F1, as usual in this kind of problem, we want to begin by identifying prime implicants, and there's no rectangular grouping of 8 one cells, obviously, nor are there any rectangular groupings of 4 one cells. However, we do have some rectangular groupings of 2 one cells, and so let's start with those. Here is 1. And that would be, I hope you'll agree that that will be x, y prime. And here is another grouping of 2 one cells. and that is y prime z. Another one is here, and that one is xz, and then that completes all of the rectangular groupings of 2 1 cells. Now we have one more rectangular grouping of one cell, and that is x prime y z prime. Now, if we look for the essential 1 cells, because our next step, of course, is to identify essential prime implicants. And so we see that this is essential, as is this, as is this, and as is this. And so since this 1 cell is essential, xy prime is essential, and since this is essential, y prime z is essential, and since this is essential, xz is essential, and then finally, since this is essential, x prime y z prime will be essential. And so now when we look for minimal sums, for f1, we have f1 of xyz, and as usual, we have to start with what is essential. So we have x, y prime, or y prime z, or xz, or x prime y z prime. And when we shade in each of those, okay, we shade in xy prime, we shade in this, and then shade in y prime z will give us this, and then xz will shade in this, and then finally x prime y z prime will shade in this. And so we see that we've accounted for everything in the function f1, so we're done. And now we stand back and look at what we've done, and we see that, well, we have made progress here, because as you will recall, f1 was originally the sum of 5 minterms, and now we're writing it as the sum of 4 terms. However, up here, we see that it's going to be necessary for us to, if we're going to use this PAL, it's going to be necessary for us to write f1 as a sum of 3 terms. So this looks like a possible difficulty for us, but before we give up, let's go ahead and move to f2 and see what we have there. So for f2, for the prime implicants, well, we have no rectangular groupings of 8 1 cells, but we do have a rectangular grouping of 4 1 cells right here. And the name of that will simply be, and this should be YZ here. The name of that will be simply Z. No more rectangular groupings of 4 1 cells, So let's move to 2, and we do have a rectangular grouping of 2 one cells here. And the name of that will be x prime y prime. So now when we look for essential prime implicants, we note that almost all of the one cells in this Carnot map are essential, and therefore both of these prime implicants are essential, and therefore when we look at the minimal sums for F2, okay, we start with what's essential, so we have Z or x prime y prime. And when we shade in those terms, okay, here is Z, and here is x prime y prime, and we have accounted for everything, and so this is the only minimal sum for F2. This is the only minimal sum for F2, just as this was the only minimal sum for F1. Now, here we've been able to we've accomplished quite a bit of simplification, because remember that F2, like F1, was originally written as a sum of 5 terms, and now we've gone all the way down to the sum of 2 terms. In fact, we've gone so far that it seems like we have maybe gone too far. And what I mean by that is that here in the PAL we see that F2 is written as the sum of 3 terms, but it turns out that to get a 0 is no problem. So let's go ahead and get started with this, solving this problem in the following way. It's obvious when you look at our functions F1 and F2, it's obvious that both of them have all 3 of the variables x, y, and z. So it seems reasonable that for 3 of our 4 inputs we should have x, y, and z. So let's go ahead and put x on the top one, y on the second, and z on the third. And we can go ahead now for F2. We see that F2 should be equal to z or x prime y prime. So let's go ahead and program that in. On this, notice that this line here makes the first contribution to F2. So let's go ahead and mark in z on that first line. And then the other term in F2 was x prime y prime. So we'll go up here to this second line for F2. Here's the second line. And we want x prime y prime. So we get x prime and y prime. Now, as I said a moment ago, we have actually a third line that contributes to F2, but that's not needed. And so what we can do in that case, when we have an unnecessary line, we can just put an x in this AND gate, and what that is equivalent to is ANDing together all of these terms on this line. And since that would involve ANDing variables with their complements, we know immediately, whenever you AND a variable and its complement, you get 0. And so this would give us 0 on this line. So if we make the 3 connections here that we've shown so far, z on this line, and x prime and y prime on this line, then at least we will get F2 correct. But what about F1? Well, the answer to this is that, we have to write F1 as a sum of 3 terms, but the problem is that we have 4 terms down here. However, what we can do is we can consider F1. Let's draw a line over here. We'll consider F1 of XYZ, which is, we've shown that that's equal to XY prime or Y prime Z or XZ or X prime Y Z prime. We'll consider that to be equal to XY prime or Y prime Z or F3 of XYZ, where F3 of XYZ is equal to XZ or X prime Y Z prime. And this will give us the solution to our problem, because notice that if we do things in this way, then F3 here is the sum of two terms, which is just what we want here. And then F1 will be the sum of three terms, XY prime or Y prime Z or F3. So we see that what we need to do to finish up making our connections is we need to make a connection here, and we're going to feed back F3 into this last input line. And now we can go ahead and finish F1. As we see here again, F1 is XY prime, so we come up here to the first, here's our first contribution to F1, so we'll put XY prime, so here is X, and here is Y prime. The second contribution to F1 is Y prime Z, and so we come up here for this second line, we want Y prime Z, and so here's Y prime, and here is Z. And then the last contribution, the third contribution to F1 is F3. And now that we have fed back F3, oh, excuse me, I'm making a mistake here. This connection, put that connection in the wrong place. It needs to be after the OR gate. So otherwise, that definitely would have been wrong. That was wrong as it was. So, because we want to OR these terms together. So now that we're feeding back F3 into this last input, and F3, as we note here, F3 is the last contribution to F1. So we come over here for this last line that's contributing to F1, and we want to make a connection with F3. And now the only thing that remains for this problem is to fill in the necessary inputs here for F3 itself. And as we said, F3 is XZ or X prime Y Z prime. So in this first line we can put XZ. Here's X and Z. And in the final line for F3 we have X prime Y Z prime. So here's X prime Y and Z prime. And that concludes it. This is the way that you would program a PAL, a programmable array logic. This is the way that we could program it to realize the two functions F1 and F2. Just that straightforward. And that concludes Lecture 20. And so now let's look at the test problem. There are two in-class problems, 20.1 and 20.2, and then there will be another one in class, 20.3. And 20.1 through 20.3 all refer to this circuit. And you notice that it's very similar to what we had above, except that everything now has been marked for you. I'll just point out a few things. The OR array down here is identical to what we had in the example we did in the lecture. And here the AND array has been chosen. And let me make sure you see all of these clearly. This is on the X line. This is on the X line. This is on X prime, Y, 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 Y. This is Y prime. Here is Z and Z and Z. This is on the Z prime line. And this X and this X are both on this line here that has F3. And so you can evaluate what F1 and F2 and F3 are equal to in this case. And then you have some questions. The first question says, this is 20.1, circle each of the following expressions that is equivalent to F1. And it says in order to get credit, you must get all of them. And so the choices are the sum of the minterms 2, 4, and 5. B is xy or yz or x prime y prime. C is the sum of the minterms 0, 1, 3, 6, 7. And D is the product of the max terms 2, 4, and 5. And then for 20.2, circle each of the following expressions that is equivalent to F2. And in order to get credit, you must get all of them. And here we have for A, x prime z or y. For B, the product of the max terms 0, 4, and 5. For C, the sum of the minterms 1, 2, 3, 6, 7. And finally for D, x prime yz or x, y, z prime. So that concludes the problems, and that's the end of Lecture 20. And so good luck.